Hello everyone and welcome back. So now for a little more difficult problem. Now you see it says group problem solving. Normally if you are in person, we will do this problem in groups. With social distancing, with other issues, it might not happen here if you're watching this video. However, if you have somebody who knows engineering, get together, practice together. If you're really good friends with people who are going through the class with you, call them. Maybe you do a Teams meeting to do this problem together and future group problem solving together. But we're going to go over here. We're going to walk through it together. But remember, you always should try these problems on your own. So first off, let's talk about it. So we have three concurrent forces acting on a bracket. Now when we say concurrent, we mean that they happen at the same exact point. They're all acting right there. We don't have some bar and we have one force over here and one force over here. No, we just have three forces acting on a single point. What do we want to find? We want to find the magnitude and angle of the resultant force. I'm going to show the resultant force in a sketch. Okay, so we see we have right here, we have a slope triangle. We have two angles. We're going to have to break it into components. We're going to add those components together and we're going to calculate the magnitude and angle using inverse tan and using our Pythagorean theorem. Do you think you can do it? I believe you can. It's very similar to example 1. So if you need to reference something, before you jump ahead and look at how they do it, look at example 1 and see if that can help you and help you solve this problem. Okay, with that, I'm going to count to 3, pause the video, go try it, and then we're going to jump straight into it. So 1, 2, 3. Okay, hopefully you're back. Let's jump into the problem. So first off, we need to break everything into components. The slope triangle one is usually the easiest one to go for first because no angles, no plugging into your calculator really. So what we see here is if I break it up, I actually need to move this a little bit lower so I don't mess anything up. And what angle are we going to take? We're going to take that one. Okay. So this is 4, that is 3, and that is 5 for my slope triangle. Though just as a note, that's going to be 850 when it's a force. And so this is the angle theta. So if I want to get the x component is going to be opposite over hypotenuse. The y component is going to be adjacent over hypotenuse. If you're confused, like, well, what if it was this thing you were talking about? In the end, it really doesn't matter because it's always going to be the horizontal component of your slope triangle will be connected to your horizontal force component. The vertical component of your slope triangle will be connected to the vertical component. Always going to be that way. So there's not really a way that you can get mixed up. Now, sometimes you have to use a slope triangle to make another slope triangle, and then things can get wonky then. But in this case, at least, this is vertical, so that's y. This is horizontal, that's x. Just keep on going with that. Okay, so you plug those numbers into your calculator, you get out 680 and 510. Be careful with your negative sign, it's pointing down. Then force 2, with this one, it's just angles. Now here's a place that's going to get you confused because you're like, wait a second, but they use sine of 30 for x and cosine of 30 for j. I thought that sine was always for the vertical component and cosine was for the horizontal component. That's not the case. You have to look at how they drew that force. So I know F2 over here, I have a theta, and I have to figure out the F2x and F2y. But if you look at this, F2x is on the opposite side, F2y is on the adjacent side. Well, opposite over hypotenuse is sine. So because of what angle they chose, since they chose this angle instead of this angle, we had to use sine of theta instead of cosine theta. That's what makes this a little bit harder. And the fact that they're trying to trick you with that. So don't let them trick you. On my homeworks, I'm most likely going to trick you several times. But that's okay because you have many different submissions. You can go back and try it again. Make sure that you've mastered this before you get to any of the assessments because I want you to do well on those. And I believe that you can do well. Okay, so next one, we do the same exact thing with the same exact little stipulation. We got to make sure that we're using sine for x and cosine for y because once again, we're not using the angle to the x-axis, which is what you're probably used to. We're using the angle to the y-axis. And with that, we get all of our components. So now everything's broken into components. We can add it together to get our resultant vector, which is going to come out to be negative 162.8 in the horizontal direction and negative 520.9 in the vertical direction. So left and down into the third quadrant. If we want to find the magnitude, we use Pythagorean theorem. C squared is equal to a squared plus b squared, or c is equal to the square root of a squared plus b squared. C equals square root a squared plus b squared. And finally, we use our inverse tan function to figure out the angle. Now, here's a point where you might be confused about, like, well, 72.6 degrees to which axis? Where is it going? Well, at this point, you can see that they made both of them positive. You see how there's no negative signs here. So you could redraw this and pretend like it's going over here. Now, if you're still uncertain, like, okay, well then still, what is it? It's always going to be from the positive x-axis if it's over here in this quadrant. It's always going to be to the positive x-axis is the one they're taking. It doesn't have to be, but it will be. Opposite over adjacent. The y over the x will always give you the angle to the x-axis. All you've got to be careful about is that you realize if they're negative or positive, what's going on there. And of course, the answer is different if you go from the positive x-axis rather than from the negative x-axis. You don't have to give it that way. I will always tell you what axis to give you an angle from. Okay, so with this, we have solved it. We've done it in record time too. So hopefully this helped you. Hopefully you're getting a little bit more of a handle of breaking things up into components, plugging into your calculator, adding them all up, and getting a resultant vector. If this didn't make sense to you, please look back over these past few example problems until it just makes sense for you. Okay, we'll stop here. I'll see you all next time. Bye-bye.